You know how large language models, or LLMs, are these incredibly powerful tools? They seem to do almost everything, writing essays, solving complex math problems, you name it. But deep down, they're often called black boxes, right? We don't fully understand how they do what they do, or sometimes why they kind of stumble.
That's true. Yeah, the inner workings can be pretty mysterious, honestly. But what if we told you there's maybe a new way to peek inside that black box? Today, we're taking a deep dive into some really fascinating new research. It explores how LLMs learn, specifically looking at something called gradients.
Gradients. Okay, so think of a gradient like a signal, almost like measuring the effort an LLM needs to put in to learn something new or adjust its understanding. And this research, it's all about understanding what happens to those effort signals when LLMs learn in different ways, what the paper calls fast thinking versus slow thinking.
Exactly. Yeah, our mission for this deep dive is really to unpack this paper. It's titled, What Happened in LLM Layers When Trained for Fast versus Slow Thinking, a Gradient Perspective.
Yeah.
It uses some pretty cutting-edge analysis to reveal how different parts of an LLM respond during training. It offers some novel insights into, their efficiency and stability, so you're going to get a shortcut, basically, to understanding some fundamental truth about how these powerful AI models actually learn.
Okay, right. So to really get what's happening inside, we need to first grasp this central idea they introduce, fast thinking versus slow thinking in LLMs. The paper kind of draws an analogy to Daniel Kahneman's work, on human thinking. But for LLMs, it basically boils down to whether they're given a detailed step-by-step reasoning process or just the direct answer.
Precisely. Yeah, fast thinking usually means training an LLM with just the final answer, or maybe a very simplified chain of thought coase. Think of it like just giving the solution to a complex math problem. Slow thinking, on the other hand, that involves providing a detailed code, a full, explicit, step-by-step reasoning path, like showing all your work, right? Sometimes that path is even generated by another advanced LLM, like GPT-4o.
Gotcha. And the researchers looked at how these gradients, those internal effort signals we talked about, how they behaved across different parts of the LLM, specifically in the attention and output layers within that transformer architecture. So what did they actually observe when they compared these two thinking styles?
Well, what's truly fascinating here, and really core to the findings, is the profound impact on learning stability. The study found that training LLMs for fast thinking, what they label non-coty, it led to significantly larger gradient values and really drastic differences in these signals across the model's layers. For instance, looking at the Quen2 1.5b model data in their table 2, the mean absolute differences, or MAIDs for non-coat, were the largest across all projection layers. That indicates pretty severe fluctuation.
Okay, so a lot more effort being signaled and maybe a bumpier ride for the LLM during learning, more turbulence.
Exactly, that's a good way to put it. This large scale and fluctuation, it might really cause instability in training. However, when those detailed code paths were provided for slow thinking, those MADs, those fluctuations, they dropped consistently and significantly. This led to much smaller and smoother gradients across the layers, which you can actually see visualized in their figure 1. It strongly suggests greater learning stability.
Wow, okay. So here's where it gets really interesting then. It's almost like the LLM is showing its work, right?
Hmm.
And that process, breaking it down, makes the learning itself more efficient and stable. This seems to align really well with the success people have been seeing recently using more detailed COTI reasoning paths for training models.
Hmm.
Absolutely. It provides some potential underlying mechanism for why that approach works so well.
So if slow thinking provides this more stable learning environment, that sounds great. But what happens when we, throw in a curveball, like incorrect or maybe just irrelevant information? Can these LLMs, through their gradient signals, actually distinguish between like correct answers and just nonsense? Yeah, that's a really important question, isn't it? It gets at the LLM's internal awareness, if you can call it that. For reasoning tasks, specifically things like math problems or common sense questions, the study had a pretty key finding. When detailed code paths were provided, the gradients could apparently distinguish correct responses from irrelevant ones. The signals, the gradients, were noticeably larger when the model was learning irrelevant information. This indicated more effort was needed for this kind of false alignment, as they put it, with its internal knowledge. You can see this pattern in their figure 2.
Okay, that makes intuitive sense. It's like the LLM is struggling more because the irrelevant stuff conflicts with what it sort of knows or expects from all its pre-training data.
Precisely. That conflict seems to register as increased effort. However, And this is crucial without Coco. So in that fast thinking mode, the gradient behaviors between learning correct responses and learning nonsense responses were almost identical. Their relative differences were tiny, less than zero point zero 0.01 according to the paper. Yeah. This suggests that without those explicit reasoning steps, LLMs really struggle to build the necessary logical connections to even identify irrelevant information. They just seem to learn it without much fuss, whether it's right or wrong.
So the reasoning steps themselves are critical not just for learning correctly, but maybe also for identifying when something is incorrect or doesn't fit. And the research also points out, I think, that the earlier layers of the LLM seem more sensitive to this nonsense, especially when Cody's present. That's shown in their table 3, right?
That's right. It suggests those initial layers might be playing a bigger role in that initial validation or checking process, at least when guided by reasoning steps.
Okay, that's a powerful insight for understanding that internal validation piece. So we see the power of slow thinking and Cody for reasoning, but what about just pure knowledge acquisition? Like, learning facts from Wikipedia or something similar. Does the same logic apply there?
Ah, that's a critical distinction the research makes, and the answer seems to be no, not really. For these knowledge-intensive tasks, simply making the answer longer, increasing the response length, it does not lead to those similar gradient patterns we saw with slow thinking and reasoning, which means, basically, longer answers alone don't give you the same stability benefits if they lack that structured reasoning process. You can see this quite clearly in their figure 4.
Right. So it's not just about the number of words, it's really about the type of information. Those explicit reasoning steps are the key ingredient for stability and error detection and reasoning.
Exactly. It's the structure, not just the length. What's also fascinating, though, in the knowledge learning part, is the effect of how popular or common the information is. The study observed that learning unpopular knowledge, less common facts, triggered significantly larger gradients and fluctuations. Again, shown in figure 4. This suggests LLMs need more effort to internalize information they haven't encountered as frequently, which kind of makes intuitive sense, right?
Right.
Popular knowledge is probably more reinforced in their massive training data sets.
Yeah, that tracks. And when it comes to spotting correctness in these knowledge tasks, do LLMs show that same kind of struggle with irrelevant information, like they did with the flawed reasoning?
Interestingly, no. It seems different. Unlike the reasoning tasks, the LLMs they tested, even the ones specifically fine-tuned on instructions, they weren't really able to identify nonsense knowledge through their gradient patterns. The curves, the gradient patterns for correct knowledge and irrelevant knowledge responses looked almost identical in figure 4. This implies that for pure knowledge, LLMs might just absorb the information presented without those same internal conflict signals kicking in like they do when faced with logical inconsistencies in reasoning.
Huh. So their internal checks for factual accuracy seem maybe less developed or operate differently than their checks for logical consistency during reasoning.
That seems to be what the gradient pattern suggests, yeah.
Okay, wow. This has been quite a tour inside the LLM black box. So let's try to pull this together. What does this all mean? Like, why is slow thinking more stable,
Yeah.
fundamentally? And what are the big practical takeaways from looking at these gradients?
Right, connecting it to the bigger picture. The paper suggests that these detailed Coty paths, they essentially make the reasoning gaps between sentences much smaller, much more manageable. This allows the next token, the next word or piece of information, to be inferred with a higher probability because the preceding context provides more necessary information. It aligns better, you could say, with the patterns the LLM learned during its pre-training. And this leads to smaller prediction errors or losses during fine-tuning and, crucially, a stable gradient signal. Irrelevant reasoning paths, on the other hand, they hinder this alignment. They create bigger gaps, leading to those larger, more unstable gradients we talked about.
Okay, so it's like giving the LLM a really clear, well-structured path. Lets it integrate new stuff more easily with what it already knows, leading to smoother learning.
Yeah.
That makes sense. And what about the differences you mentioned between the base LLMs and the instruction-tuned ones? That was surprising.
Yeah, that was quite interesting. The research found that the instruction fine-tuned LLMs didn't necessarily show a superior ability in identifying incorrect reasoning paths via gradients. What's more, sometimes these instruction-tuned models actually required more effort. They showed larger gradients when learning simplified Coty paths compared to the original pre-trained base models. That's in figure 3. This kind of highlights that the instruction tuning process itself, the data used for it, might create its own set of biases or discrepancies that impact how new reasoning, even simplified reasoning, gets integrated.
That is a surprising finding. It suggests that alignment tuning isn't some kind of silver bullet for improving every aspect of model behavior, particularly this internal error detection.
Exactly. It adds another layer of complexity to understanding how these models evolve through different training stages.
So zooming out then, what are the potential applications? How can we actually use this understanding of gradient behaviors in like real-world LLM development?
Well, this raises the important question. How can we leverage this? Firstly, these gradient behaviors, they could potentially be used as a signal, maybe to evaluate the quality of training data, like how compatible is this data with this specific LLM? It could help us select better data for fine-tuning, maybe data that leads to smoother gradients. Secondly, understanding which internal layers are most sensitive, showing the biggest gradient changes, could help identify potentially critical layers for certain tasks. This might lead to more efficient or targeted training strategies. And finally, just fundamentally, these patterns offer deeper insights into the unique characteristics, maybe even the internal biases of different LLMs. It helps us decode a little bit more of that black box.
What a fascinating deep dive. Okay, so today we've really gone beneath the surface of LLMs, haven't we? Learning how their internal effort signals, these gradients, reveal some really interesting differences between fast thinking and slow thinking.
Yeah, we saw that explicit step-by-step reasoning, that detailed chain of thought, seems to lead to more stable learning. And importantly, it even seems to help LLMs internally detect incorrect or irrelevant information, at least in reasoning tasks. But we also learned that this doesn't just automatically apply to pure knowledge learning. Simply making answers longer doesn't achieve the same effect there, and LLMs might struggle to identify factual nonsense through these gradient signals alone.
It really makes you think, doesn't it? If LMs learn more effectively, more stably, when they're guided through a detailed reasoning process with clear, small steps. What does this tell us about how we learn and maybe, the inherent value of actually showing our work, breaking down complex problems, not just for getting the right answer, but for the learning process itself? It certainly offers a fresh perspective on the power of explicit reasoning, both for us humans and apparently for our AI counterparts too.